Welcome to Innovation Alley. Today's discussion is on new regulatory drivers and emerging technologies with biological wastewater treatment with AGS.
Hey, we are in Rockford, Illinois today at the Aqua Aerobics Research and Technology Center, and today we are excited to be talking about wastewater treatment, the latest advances in biological treatment that are out there in the industry. I'm excited to be here and joined with several guests today. I'm Dave White, the wet weather practice lead at Wade Trim. With me is my co-host, Vin Rubino.
Yeah, Vin Rubino, I'm the wastewater treatment practice lead for Wade Trim.
Hi everyone, I'm Joe Tardio, product manager for Aqua Narita Aerobic Granular Sludge Technology here at Aqua Aerobic Systems.
Hey everybody, my name is Ryan Messer. I'm with HDR. I'm their Florida Re's practice leader and a project manager.
Hello everyone, I'm Terry Reed. I'm the Director of Research and Development for Aqua Aerobic Systems.
So we're excited to bring together two groups today, the engineering industry as well as equipment suppliers and vendors, to talk about what is happening in this area of biological wastewater treatment. Vin, could you perhaps give us a background on what wastewater treatment is for our listeners that are out there?
Sure, I'll start with a brief history. We'll start with the Clean Water Act of '72 and a massive investment by the U.S. in its treatment plants across the United States, starting with basic secondary treatment. Biological treatment was conventional treatment, a lot of mechanical systems, including settling and filtering and some getting the big stuff out of the water. And that brought us through most of the 70s and 80s. Regulations started to change, requirements of water quality were changing, biological nutrient removal became a bigger thing. So you had to remove nitrogen and phosphorus. The treatment train changed because of that, and as regulations changed, requirements of water quality changed, technology had to change. So we'll be talking about some of that technology change today. Now we hear about people needing to treat more water, more wet water, storm water, all that's getting into our sewers, has to get treated at the plants. We hear about emerging contaminants, things that we never talked about in the 70s and 80s. We're talking about PFAS now, endocrine disruptors and the like. So we've changed the biological treatment accordingly. And we've got Aqua here to talk a little bit about what they're doing at this facility and others.
Yeah, and so that's part of this whole emerging contaminants, right, Vin? And there's different ways that we have out there that we can treat these kind of specialty contaminants. Does anybody have any ideas on how to do that?
Yeah, well certainly, one of the technologies we're focused on, and I'm solely focused on, is Aqua Narita Aerobic Granular Sludge. And one of the main reasons that it's looked at is because of the high rate capacity that the technology offers, in addition to the ability to treat for enhanced nutrient removal. So when we look at nutrient removal, we're looking at low levels of total nitrogen and total phosphorus, but ideally able to do those with little or no chemical addition, as well as treating to a high standard to allow for things like indirect potable reuse in some areas of the country. And we look at coupling that treatment capability in a way that allows for either existing plants to supplement capacity while treating to a higher standard, or actually new plants in order to enable treatment either in a retrofit, a brownfield, or even a greenfield situation for a brand new plant sort of advanced wastewater treatment process. So lots of different applications we hope to speak about a little bit more today.
Yeah, and then this is one of many technologies that's now part of a wave called intensification, needing to do more treatment in a smaller footprint, saving energy, and the technology has changed to meet this challenge.
I think, to your point earlier, that these facilities that were built in the 70s, in the decades that have gone on, the regulations have increased, the communities have built up around the wastewater treatment plants, the regulations have become more stringent, and so everybody's looking at creative ways to try to do more with less. And intensification is a concept that we're hearing quite a bit, and we kind of look at that from a whole plant perspective, not just a biological process. And Another technology that plays into that is advanced primary filtration. And we've coupled that with the Aqua Nerita. With advanced primary filtration, it's a way to replace some of the larger primary clarifiers with a solids separation device that takes up a fraction of the footprint. So we're looking at it not just in the biological area, which obviously would provide the greatest gains in terms of footprint recovery, but I think it goes plant-wide. And from primary to secondary to tertiary treatment, looking at creative ways to recover that land and increase capacity, meet the regulations in a way that's resilient as well.
Yeah, what's driving this? Is this development and the plant needs to expand, or is it perhaps wet weather that's overwhelming an existing facility?
I think those are all good points. Depends on each case. A lot of it is regulations. As plants start to go from nitrification only to total nitrogen removal and lower levels of total, and as well as phosphorus removal, that's affecting the biological process. So plants that had conventional activated sludge historically have to look a different way, either a multi-stage process, but that doesn't really recover the footprint. So the intensification processes like the Nerita process are one way to do that. So certainly the regulations, the increased capacity that has grown over the years while the plants haven't, and so those are a couple of areas that are driving these decisions to look at creative ways to implement new treatment technologies.
Yeah, and I can add, even in coastal areas, in my perspective in Florida, we're seeing so much population growth now, and we're not seeing much municipal overtake of new property. So trying to do what you can within your current wastewater treatment plant footprint, but also being able to advance systems for non-potable reuse, or offsetting potable water irrigation issues, or going to tackle the issues that we have with blue-green algae with any surface water discharges or other impacted waterways in that way. Just to lessen total nutrients provides a great value to our environment in itself.
Yeah, and the blue-green algae problem, could you maybe describe that a little bit for folks that maybe aren't familiar with it?
Sure. In Florida, we see this in a large-scale problem area. It's just simply nutrients being added to water with the addition of chlorophyll, photosynthesis occurs, and boom, you have an algae issue. That's not to say that algae is always bad, but toxic algae can become such. So we try to lessen the total algae that can grow by lessening the total nutrient contribution to receiving waters that are affected by the wastewater or the reclaimed water that we would put out into the environment itself. So thereby lessening the total nutrients within wastewater, within effluent wastewater or reclaimed water, as we would call it lovingly in Florida, we would thereby be helping out fish populations, help with seagrass levels, help with many aspects of water ecosystems.
Yeah, and another great example, local example, where we're sitting right now in Rockford, Illinois, in terms of nutrient removal. This facility, which is a conventional 40 MGD facility, discharges to the Rock River, which is an important protected ecosystem here in northern Illinois. And so this utility, Fall River Sanitation Authority, is actually currently, as we speak, implementing both Aqua Prime, which is advanced primary treatment technology, upstream of Aqua Nerita, in a parallel treatment configuration where that Aqua Prime will not only take load off of the current conventional activated sludge facility, but also pre-treat for the Nerita system, in addition to the enhanced carbon diversion for their anaerobic recovery system, but also allow for the blending of those two effluents, conventional effluent as well as the effluent from the Aqua Nerita aerobic granular sludge, in order to produce a higher level nutrient effluent, or treat to a higher level of nutrient standards in order to reduce the nitrogen phosphorus load to that Rock River ecosystem. And I think it's important to understand how forward-thinking this utility is being, not only to meet treatment limits of today, but the anticipated regulatory limits that will come in the next 10, 15, 20 years. So making the infrastructure investment today will put them in a position to meet those limits, 20, 30 years down into the future.
That's a very good planning idea, because you don't know where regulations are going. We said nobody saw this in the 80s and 90s, and you don't know where it's going in the future. So you're taking a step now, and you've got the ability to ratchet it up in the future if you need to. So it's a stepwise thing, and that can fit a lot of planning ideas, right? So you've got to focus on an immediate regulation. So you meet that. You don't have to go all in with a whole new system. You're just supplementing the treatment you've done now, and then, as you said, blending to get where you need to go.
Sure.
The other thing that you mentioned intensification before, there's a real drive in many plants to save energy. Aeration systems are typically the biggest energy consumer in any wastewater treatment plant. And these systems are now saving a lot of oxygen, a lot of energy because of that.
Yeah, I'd say there's the biggest energy consumption to me could be with trying to achieve any level of intensification, could be through an MBR type facility, a membrane bioreactor. In essence, you're getting rid of your clarifier and your separate filter, and you're putting that into a single MBR process, but that requires a lot of oxygenation and a lot of energy to be consumed through that. So there's that cost balance. There's also a TOC benefit, but that's for your own determinations as municipalities to figure out what's best for you. But otherwise, for intensification, you could get back towards densifying your activated sludge. This can be done through many ways of your traditional aeration basin and clarifier recycle streams through return activated sludge by essentially selecting the thicker solids to return them back to the basin and wasting the lower sized particles. And that can be done in a few ways through hydrocyclones on the return stream, or it can be done through lamella plates, or even in sequencing batch reactors, which are essentially the combination of aeration basin and clarifier. That can be done through surface wasting to just densify. But what we're seeing now with aerobic granular sludge is a different level of granularizing sludge to a much higher density, and with its inherent, much more consistent benefit of nutrient removal. Within these granules that we love to see is all three types of zones that you would see within a secondary process, be it anaerobic or anoxic or even aerobic, all within a core mantle and crust type of formation of these granules. And in essence, one sequencing batch reactor with aerobic granular sludge, low aeration control, and overall monitoring and optimization provides for really low effluent nitrogen and phosphorus levels while being able to avoid the need for conventional processing of aeration in separate clarifier zones. And that's not to say that conventional processes would be not what you would want to choose if you needed to upgrade something. It's up to your existing infrastructure and how you would be able to use it. But say you are a conventional process and you would want to add nutrient removal to your system. If you just have a single stage aeration basin, you would need to add 2 or 3 stages in internal recycle to those systems in order to give yourself the nutrient benefit. In this way, for a sequencing batch reactor, you can achieve the same thing at about a 60% total footprint that would be required for the same nutrient concentration removal effectiveness.
Less footprint, less money, more room to do other improvements or expand in other places.
Yeah, less concrete. And I also see this as a solid benefit when you partner with Aqua for the way that you implement design. There's engineers that have boots on the ground. There's folks like Joe that also provide a solid level of continuity. You have calls with them every week or two, making sure that you guys, that both the engineer and the consultant and the owner are all on the same page with how this process is going to be implemented. The balance is done right for water quality and quantity, and you're getting that vision towards the current treatment requirements in the future as well. It's a lovely thing to see.
So Terry or Joe, which one of you trained the granules to do all this stuff in one spot?
That would be Terry.
Well, it's something that, I came from the conventional sequencing batch reactor marketplace, and we had decades of experience in that. So really, when I started looking at the Narita process, I was a little bit, well, can that really happen, and is that really providing a benefit? And I think you make a couple interesting points that are oftentimes overlooked in terms of the aeration energy. With respect to historic operation of sequencing batch reactors or even multi-stage systems, we look at discrete control of the aeration system. You have historically be maintaining a 2 milligram per liter residual DO for nitrification, and then making sure the DO is below a half a part per million or lower for anoxic condition, and the conditions are right for anaerobic treatment. With the Narita process in developing these granules, we have that ability to control those environments, but we don't necessarily have to subscribe to the historic practice of aerating to 2 parts of DO and bringing that down. So we can really operate the system with a much more finite control, operate low dissolved oxygen, save some energy, and we're still going to support the nitrification and the denitrification and the phosphorus removal within. The other part to that is we are taking all this biomass, and not only are we going from 3,000 or 4,000 milligrams per liter to maybe 8,000 to 10,000 milligrams per liter, we're packing that up in these granules that are typically in the range of 0.6 to 4 millimeters in diameter. And so what that means is the bulk liquid is free of solids. And so when you do oxygen transfer with the diffusers at the point where the air is released, it's transferring into water, which has a lower viscosity than conventional activated sludge. So we are able to maintain this high biomass concentration without necessarily dealing with the added viscosity and reduced aeration potential that you'd see in elevated mixed liquor applications.
Yeah, and that becomes really important from an holistic energy kind of profile of the plant. And this plant is really a perfect example of that. So when you talk about, energy efficiency, we're talking about aeration, right? So we're also talking about the ability to produce energy. At this plant, they use anaerobic digestion for offsetting the energy consumption requirements of the plant. And so when you look at the new treatment train that will be installed, which is essentially in parallel to their conventional, you have several areas of either energy optimization or enhanced energy production. So you've got the organic load that the Aqua Prime advanced primary treatment will take off of the conventional facility, thereby reducing the energy consumption on the conventional side. You've got the increased energy production that now that BOD load transferred to the anaerobic digestion facility will produce. And now you've got a super energy efficient advanced treatment system in the Narita process that will deliver advanced nutrient removal at about 50% energy consumption of the conventional system. So you've got 3 areas across an entire treatment plant that are increasing in terms of energy efficiency, in addition to enabling the utility to produce a higher quality effluent. So it's really a kind of a state-of-the-art type of process to look at from that perspective.
And it didn't start out that way. We started looking at the primary side of the treatment works about 2014, 2015, and taking a technology, cloth media filtration, that has historically been used in reuse and tertiary applications, and we asked the question if it could be used on primary solids, and we weren't quite convinced it would. But we did that first testing here at the Four Rivers facility. They weren't convinced at that point, but then we took that technology out to California, and we're now on our 4th program with the California Energy Commission to evaluate advanced primary treatment, and specifically advanced primary filtration, to increase the solids reduction, which what we saw here at this facility, that the clarifiers were moving 65% of the TSS, and with advanced primary filtration, we bumped that up to 80 to 85% removal of TSS. And then with that goes the removal of the organic material that was typically about 40% removal here, and we were seeing closer to 50 or even higher percent removal. And that all translates down to in this case, the Narita system. And so the district or the authority, in learning about the Narita and primary filtration, separately kind of pursued each of the technologies, recognizing that the value can bring in terms of smaller footprint, reduced O&M associated with it, but yet having that energy savings component.
So one other valid point on that, to add on to that, and especially what Ryan said about densification and process intensification, to Vin's point as well, Something that Four Rivers will be able to do with their infrastructure upgrades is actually send the wasted sludge produced by the Narita system to their conventional system. And through previous work and testing done with us as well as Four Rivers consultant Black and Veatch, it was determined that doing so would actually enhance the settleability at their aeration basin sludge of about 20%. And so that's something that people don't often think about, is actually the sludge that we're wasting from the Narita process is actually densified sludge. So what typically conventional systems are trying to produce, we're actually wasting from the Narita plant and can supplement an existing facility if you're looking at parallel treatment in order to increase, either increase capacity and or decrease operational costs.
So the Narita sludge is actually acting as coagulation, flocculation in the settling basin.
Yeah, that's correct. Yeah, so we're actually wasting fine, in some cases, small, very small granules or very rapidly settling flocculent sludge. And Terry's done a lot of work on this basis.
And to your point before, in terms of developing the granule population, there's always the thought that, well, bigger is better, that we would end up trying to grow the granule as big as you want, as you can. And there's some truth to that to some extent, but there's also some benefit in kind of managing it within an ideal range. And so when we operate the system, we're looking to maintain granules that are maybe greater than 70 or 80% of the biomass is in granular form. So they're larger than 200 microns. But in reality, we're trying to hone in on that sweet spot and somewhere between, say, 600 and 1.4 millimeters, maybe 2 millimeters, where we can get the benefits of that biome where it provides nitrification, denitrification, bio-P removal. And so from that standpoint, we're focusing in on being able to tailor the performance of the system. And as a result, the material that we end up wasting is fairly dense and probably would be very good settling material at any activated sludge plant.
How do you control the granule size, Terry?
A lot of it has to do with different levers that we have in the process. Being a batch system, we can control aeration, we can control the timing and the cycle times, for example. We can control the feed rate. So there are different things that we can look at to try to do that. And ultimately there'll come a point where you're wasting not just flocculent sludge, but maybe some of the granules. We've actually operated that facility to 15 grams per liter, mostly 80% granules. And that's not somewhere you necessarily want to operate, but from a research and development standpoint, we were interested to see if you could do that. And at that point, you're going to waste some of the heavier material. So there's different ways to be able to control the biomass. And being a batch system, it really offers that flexibility.
Yeah, it's something impressive that I see with the settleability. Just the proof really is in that settling. And sometimes it can be 5 times, 10 times higher, faster than a conventional activated sludge itself. And one thing that I think really helps with control is influent buffering. It's great that you guys don't shy away from that type of an assertion into design. It really helps. An influent buffer essentially is an inflow and equalization tank, so as to help manage wet weather, but also help control the flow that would be going into a series of sequencing batch reactors to really help maintain consistency of the process hydraulically and treatment-wise. So in essence, you have a tank that would provide a limit in increasing efficiency on the total process with the aeration and the equipment and automation controls.
Yeah, we look at various options on how to set up a system to be, the most cost effective and also meet the treatment goals that are provided to us by the engineering client. The use of pre-EQ most of the time comes down to just an economic evaluation. So when we're able to use EQ in some cases, because of how we can attenuate the diurnal peaks and load, we're able to shrink the reactor size and thereby reduce the overall cost of the system. A lot of that has to do with what the eventual treatment goals are, what the construction costs are, how large of a facility it is, what the hydraulic profile of the plant looks like, and so on and so forth. But that's really where we try to draw upon our experience from an installation base and also from an R&D perspective and understanding where those efficiencies lie. in practical terms.
Speaking of size of facilities, what are the range of installed facilities that you have to date?
So the Narita process has been installed for the last, coming up on 20 years globally. The largest actual installation is in Dublin, Ireland. It's about 160 MGD average flow with a peak of about 300 MGD. In the U.S., as we all know, and U.S. and Canada, a relatively conservative market, highly regulated. And so everyone kind of wants to see starting from smaller plant sizes. So right now, largest is about a 6 MGD, 8 MGD facility, but it's worthwhile noting that we've got maybe 20 or 30 facilities that are kind of pre-selected around the technology, some of them up to 50 or so MGD in capacity that we should see converting to orders over the next several years. So it's gaining traction. It's essentially established in the small to medium size range and is kind of pre-selected for many of those larger facilities as well.
And now we are underway with a design in Nebraska for a processor that's around 140 MGD, taking the load for that for peak, which is going to be awesome for America to have that as the largest plant.
That's right. Yeah, I should not fail to mention that with a HDR friend sitting here. That will be one of the largest facilities actually in North America, and it's amazing that they've selected and are progressing down the path of designing around the Narita process, which is an honor for us. So.
Yeah, in a lot of our applications, we've seen for early designs in the order of 2 to 6 MGD, and that is a really good sweet spot for evaluation, and one that fits many plants across the country.
Yeah, from an innovation standpoint, and this is kind of Aqua's, it's died in our blood, so to speak, is innovation. I think one thing, though, that maybe is a misperception when people speak about technology innovation in the water wastewater space is innovation is equivalent to higher risk. And that's something that we're always looking to deal with head on. How do we, as an equipment manufacturer, how do we address those points? Because they're valid concerns. Certainly there have been technologies implemented in the past that have not produced to the claims that they have produced to. So I think that's why facilities such as this, and you can look behind us, all the research and development we've done on cloth media filter over the last 20 plus years. But the fact that we also implemented our Aqua Narita demonstration facility on this site. When we implemented that facility and when we designed and installed it 4 or 5 years ago, the technology was already well vetted and proven across the world. The facility in Dublin had already built their phase 1 facility at that point. We decided to build it because of confidence building, really, in terms of the North American market, knowing that people would want to see it firsthand and not travel to Europe. But also it enabled us to just develop a suite of tools from an R&D perspective that not only are academic and great for white papers, but are also directly applicable to what we do in the field from a full-scale treatment system perspective.
I think it was also important for us to have that facility to be able to address the questions that our customers would ultimately have to us. For example, it wasn't just a matter of building the facility. We started off with the conception of it, the design, the construction, the equipment installation, and then startup. But really a big thing from my perspective was how to start this thing up in the middle of winter. So we obtained seed sludge from the Hammerwald facility in the Netherlands in August. It had already taken some time to get to the US. We stored it for 5 months before we actually put it into the facility. And so that gave us an opportunity to understand, would the morphology of the granules be sustained over that time period? And would it be effective when we seeded the system? And do we even need to seed the reactor? But these are questions that would be posed to us, so we had to do it ourselves. We did seed the reactor in late December, early January, and started the facility up on January 8th of 2018. And so now the next job came to us to understand, okay, once you've started up, how well does it acclimate? How long does it take for you to come into compliance? And how long does it take to grow granules from your seeding point to the target point. So all of these are questions that we were able to figure out in that first 6 months, the critical 6 months of the facility. Now, keeping in mind that we brought to the technology about 3 decades of experience with biological treatment and sequencing batch reactors, but yet this was important for us to understand. And today, now we can talk directly to our customers about their experiences that they're facing in the field as they start up a system, and we were able to do it, and we could share that knowledge with them without having to rely on the other facilities across the globe to be able to answer that question for us.
Yeah, I believe in one of the first plants started up in America, in Kansas, we saw the granules reach maturity in having a general startup time of about 8 months, which was really good for the data that was collected, and now the plant's been running for a couple of years, and it's really fine-tuned. And one thing that strikes me is the data that has been collected as this Narita process is being implemented in Florida is the wealth of data that's there and permitting that's required across states just to get a handle on the guarantee of the process being able to work. Comfort by the regulatory agencies, your DEP, your DEQ, that would allow the approval for this process to be implemented. And we've been able to help facilitate that process in places like Kansas and North Carolina and now Nebraska, just to be able to walk through that. And Aqua provides so much supporting information to allow this permitting process to just be facilitated easily.
That's a really interesting point too in terms of expectations of the technology. So globally, it had been installed pretty extensively, but here in the US, we run into AWT standards with 3 milligram per liter total nitrogen or 5 milligram per liter total N. These are limits that aren't necessarily applied throughout the world. And I go back to some of the first plants that we were involved with the 3 milligram per liter total N back in Florida in the Panhandle, and starting up SBR systems in the 80s to be able to do that. And we saw the value of time-based batch control there. Now fast forward 3 decades, and that was a big item for us, was to demonstrate with the demonstration facility, and then later with some other piloting in plants, of how low the system could reach in terms of total nitrogen, specifically for those type of objectives that we run into here in the US.
Yeah, quite often we're asked, and it's one of the luxuries of having a facility like our demonstration plant, quite often we're asked, well, what are the limits of technology that can be achieved? And to be able to test those far beyond what existing plants are doing, it's difficult for us to be able to go to an operating facility that has to comply with the permit and say, we would love for you to run this plant beyond your design conditions so that we can tell other people what it could actually do. And they would say, thank you very much, we love you, Aqua, but no. And so to have the ability to do that here, when engineers and clients ask us, how achievable is this limit, is really kind of an invaluable asset to us.
Yeah, and temperature, wastewater temperature can be a really key factor in that challenge, right? So with warmer weather, you get much better of a process, and then with colder weather, like we're seeing as snow today, that kind of lessens the guarantee of a nitrogen or phosphorus reduction. So do you guys have a handle on the range of temperature that you really need to see, or is there a judgment of bringing a facility indoor versus outdoors?
Yeah, we have reams of data. I think we're lucky to have a plant that's located in Illinois, because a lot of the data that we generate here is applicable for many plants across the US. We also rely on our 30 plus years of biological experience. A lot of the fundamental sizing and design tools that we use for Narita are no different than our Aqua SBR that's been, we have 1,200 installations now over the past 30 years. So the kinetics, the basic kinetics of how the microorganisms are operating are virtually the same. The other thing that we will do from time to time is run a pilot if there's a unique circumstance. One that comes to mind is we have a recent prospective client that was interested, and they're located in Saskatchewan. So they were particularly curious about how the technology would operate at as low temperature of about 5 degrees C. And so we took one of our mobile units and piloted in Saskatchewan, and to their amazement, it substantially outperformed their conventional activated sludge facilities. So from time to time, we will do mobile pilots either for an industrial client or for a very unique municipal application like the one that I mentioned, to continue to demonstrate the treatment effectiveness.
So I think we're getting close on time here, and maybe just get some closing thoughts on where the future of AGS or biological treatment may be going, pushing that envelope. These regulations continue to come on as we continue to learn things every day. I know, maybe starting with Joe, where do you think we're going?
Yeah, so I think we could talk about where things are going for probably a couple more hours here. For a lot of people, the process is still relatively new, and so I would say that kind of the future is now. For a majority of plants out there, they're still conventional treatment facilities, and so even looking to do nutrient removal is new to a lot of folks around the country. And so, we're always in that. A lot of our plants are upgrading from a lagoon plant or an oxidation ditch, and so for them, and any advanced treatment process is the future. So from that perspective, the other perspective I think is that we're going to continue to see increased regulations from the nutrient side. Specific to Florida, we certainly see the advanced water treatment 5531 continue to play out. Probably as well as on the non-direct reuse, non-potable reuse point of view, where one thing that we haven't spoken about today is the coupling of our Narita process with cloth media, not upstream of the Narita process, but actually downstream where it was initially brought to the market in the 90s. And so the combination of that process being able to comply with things like AWT standards at a much lower cost than other advanced treatment technologies would provide. So those would be my thoughts. The one last parting thought is on this general industry trend of process intensification, looking at things like densifying sludge in a conventional flow-through format. I think what Narita does is very different than that, although the densification and flow-through format certainly has a lot of advantages where a Narita process would not be implemented. And so I think just understanding where those differences lie and what the benefits and also drawbacks of both of those portions of the industry come out. So, yeah, Terry, do you have anything on that?
No, I think you said it well. I think there will be continued interest in the intensification concept, and probably not so much from the Narita perspective, because ultimately it is the ultimate densified process, being able to not only maintain that high rate settling, but operating at 8 or 10 grams per liter does provide you that ability. Where I see a lot of the focus biologically is in the existing facilities of filter activated sludge plants, where they can look to maybe see incremental changes in terms of adding capacity or whatnot. But again, it's kind of as Joe mentioned, a big difference between granular sludge versus densified sludge. I think what we'll also see is, like I mentioned at the beginning, kind of a view of the plant holistically to find out where the low-hanging fruit is in terms of not only footprint, but energy savings, energy recovery, and process steps that can help to improve performance. And I think the primary side of the treatment plant is the low-hanging fruit. We'll start to see advanced primary treatment technologies focus there, in addition to the biological. And so for us, this facility here in Rockford is one of the few plants in the world that will actually tie that into advanced primary filtration, aerobic granular sludge, to really offer the smallest footprint and most intense process that you can get in a given area.
Brian?
Yeah, I see the future of wastewater treatment really pushing more towards increasing automation and controls. We're getting better at that over time, and we're not going to stop innovating. You have too many engineers, too many manufacturers, too many visionaries that just want to keep pushing the boundaries. So as we do that, we're going to, where potable reuse is needed in areas that have those drivers for water scarcity or overall water supply, they're going to want to keep feeding their issues with wastewater plants. But the footprint of those wastewater plants, the fence boundaries, may not be able to change. So being able to intensify and get systems like this that are proven and reliable into the facility now may help when you're planning for an ultimate build out or an ultimate end use, like potable reuse schemes that may need some additional processes on the plant to be accommodated.
All right. And Vin.
Yeah, let me close by saying, Terry mentioned before, doing more with less. As a consulting engineer, I'm glad we have more tools than we had back in the 80s and 90s. And we couldn't solve some of the problems today with conventional treatment. We need things like AGS to be able to do more with less, use less energy, use less footprint, and solve increasing challenges of regulations and other things.
All right. Well, thanks for being with us today, and we look forward to catching up with you in our next podcast.